Hi, the aim of this video is to explore the physics of a guitar string in more detail than they can teach you at school. We're going to derive a wave equation, we're going to use some calculus, it's going to be great. What we're going to do now is find an equation of motion for the string by applying Newton's second law. F, the force, is equal to mass times acceleration. But this is all very easy if you have some nice point mass and a force acting on it. But what we have is a continuous string, and what we're interested in is how each bit of the string moves relative to each other bit of the string. So we need to break that down. So we've got some point masses to which we can apply F equals ma. So this is where calculus comes in, because the whole essence of calculus is that you break down something that is continuous into finite little bits, and then you take the limit as the size of those bits tends to 0 and the number of those bits tends to infinity. So, okay, here is a model of our string. Each of these blobs is a bit of mass, which I'm going to call mass delta m. And at some point I'm going to take the limit where delta m gets smaller and smaller and smaller, and the number of those masses tends to infinity, and that'll be our sort of calculus coming into things. For the moment, we can just think of them as individual point masses. And if I can find, when I choose one of these and make it special, so that one I've just highlighted red, if I can find an equation of motion for that, then I'll have the form of an equation of motion for all of those masses, for any of those masses that I like. So I'll have a general equation of motion for the string. So what sort of forces act on that? Well, when the string is just sitting there at rest, there's a tension pulling that to the left and a tension pulling it to the right over there. And at the moment, those tensions are going to be equal and opposite, and it's just going to be sitting there, not accelerating at all. But if we were to displace that string, or a wave were to pass along that string, then we'd have some displacements, and those tensions would not be equal and opposite, and they'd start to have a vertical component. So what we're going to call the y direction. So let's move some of those bits of string. Let's move that bit of string up, and that bit of string up a bit further, and this one up further still, and this one up further still. Okay, so now we've got forces with y components, and they are not equal and opposite, so there's going to be a resultant force on that red highlighted mass, and we can work out what the size of that resultant force will be. Okay, so what I'm going to do now is just go back to that diagram, but I'm going to annotate it a bit. So firstly, let's just label my little bits of mass as having mass delta m. So that's mass delta m, that's mass delta m, that's mass delta m. Okay, where are they? Well, along the x-axis, they are separated by a distance delta x. So I'm going to call the position of this one x, the position of this one that I've highlighted red, the one I'm going to find the equation of motion for, x plus delta x, and then the next one is x plus 2 delta x, and the one after that would be x plus 3 delta x, and so on. Okay, they've also got y positions. So this is y of x, the value of y at x. the value of y at x plus delta x. So that's the value of y for our red highlighted mass, and the value of y at x plus 2 delta x. Okay, I'm going to label one more thing, which is angles. Oh, also the tensions in the string. So we've got tension T pulling down and to the left with the way I've got my masses arranged, and also tension T moving up and to the right. Now, we're going to make a couple of assumptions to make our life simpler. And really it's only one assumption, but it's going to lead to a couple of consequences. And we're seeing this here. I'm assuming that these tensions T have the same magnitude. So they're not in the same direction, but they have the same magnitude. So what am I really assuming there? Well, clearly, if I were to stretch the bits of string, you can see that on my diagram, this bit of string here is stretched more than this bit of string here. So therefore, one would say that according to Hooke's law, for example, you'd expect a bigger tension in the bit of string that's been stretched more. But what we're going to assume is that the amplitude of our displacements of the string is small, so that that extra stretch doesn't really make any difference compared to the tension that the string was under in the first place when you turned the tuning pegs and tightened the string. So we can just assume that that tension is constant in magnitude and is equal all along the string. Okay, that assumption that these displacements are of small magnitude is going to allow us to do one more little mathematical simplification in the next step. Okay, labeling one more thing then, I'm going to label the angles in these triangles. So I'm going to call this angle here theta 1 and this angle here theta 2. And now we've got all the labels we need, we're ready to start doing some maths. So if I think about what is the force acting on my red highlighted mass delta M. Okay, and I'm only interested in the force in the y direction, and then I'm going to say, well, that must be equal to delta M times the acceleration in the y direction. So I'm applying F equals ma in the y direction to that mass. So how big is that force? Well, we've got a component of this tension here that pulls upwards on that string. And that component is the opposite side to this triangle, so it must be T times sine of theta 2. So this is just taking components of vectors. And then we're going to have another component, a component of this T here, which is T times sine of theta 1, because it's the opposite side to theta 1 of this triangle. And those are going to be subtracted from one another because one's up, one's down. So I can write F is equal to T sine theta 2, that's the component of the force, the tension that is pulling upwards from that up and right tension, minus T sine theta 1, which is the component pulling downwards from the down and left tension. Okay, now that is a bit of a pain having those signs in there, because sine is opposite over hypotenuse, and the hypotenuse, well, would be this height squared plus this squared, all square rooted. It all gets a bit ugly. But if we come back to our assumption that we have small amplitude oscillations, that we're only displacing it in the y direction a little bit, then that means that these angles theta 1 and theta 2 would be small angles, and we can use small angle approximations. On my diagram, they're quite big angles, but That's because it makes the diagram and the triangles so much more clear if we can draw them as quite big angles. But really, they'd be tiny angles. So we can use sine theta is approximately tan theta. So I'm going to rewrite my force in the y direction as t tan theta 2 minus t tan theta 1. Okay, now let's rewrite that, instead of in terms of these angles, theta 1 and theta 2, in terms of the y and x values. So I can write this. Okay, let's see what this looks like. So we've got f is t, and then the whole of this bit here is tan theta 2. So tan is opposite over adjacent. So we have the opposite, which is the height of this triangle here, which is yx plus 2 delta x minus yx plus delta x. So that's the opposite side. And the adjacent side to, oh sorry, wrong triangle. The adjacent side here is just delta x, because that's how far in the x direction my little bits of mass delta m are separated. And then over here I've got the same thing for this triangle down here. So I've got t tan theta 1, so that's opposite side, x plus delta x minus y of x, over adjacent delta x. Here I've just got the same thing written out as I had on the previous page, but with a couple of bits highlighted in different colours. First, I'm going to take out a factor of t over delta x, just to tidy things up a little bit. Okay, now I want to look at what I've got in the brackets there. So I've got y of x plus 2 delta x minus y of x plus delta x. In other words, that's the change in y, so delta y, with one step delta x. So when I make one step delta x, it's how much change in y I have. And the red bit here, that's also a change in y with one step of delta x, but it's the previous step of delta x. So it's going from x to x plus delta x instead of from x plus delta x to x plus 2 delta x. So the whole bracket is one change in y minus the previous change in y. In other words, it's the change in the change in y. So I'm going to write that as delta delta y. Okay, that looks much neater and simpler. Now I'm going to apply F equals ma. So I'm going to make that equal to the mass of my red dot, which was delta m, multiplied by the acceleration in the y direction. So the acceleration in the y direction is the second derivative of the y position with time. So that means it's delta m times d2y dt squared is equal to my force. So that's just Newton's second law, F equals ma. Now, if you haven't seen before this slightly curly d here, that means a partial derivative. So that means we're changing the variable t, but we're keeping other variables, in this case x, that y might depend on, the same. But don't worry too much about that if you're not familiar with partial derivatives at the moment. Okay, delta m. What is delta m? Well, all of our little delta m's must add up to the total mass of the string, which I'm going to call capital M. So I can say capital M, the mass of the string, is equal to n, which is the number of little bits of mass, times the mass of each of those little bits of mass. And how many of those little bits of mass do I have? What's capital N? Well, if we take the whole length of the string, L, and divide by delta x, the separation of those bits of mass, we must get the number of bits of mass. So we can write big M is equal to L over delta x times delta M. Rearranging that, we get an expression for delta M. So I'm going to substitute this expression for delta M into my equation here. So I get this. So here's what I've got so far. And I'm going to tidy up a little bit by dividing both sides by delta x. So I get all my delta x's on one side of the equation. So that's what I get here. I'm then going to do two things. First is just a little tidying up. I'm going to take this m over L, which is the mass of the whole string, divided by the length of the whole string. And I'm going to give it a single letter to represent it, which is the mass per unit length. So in other words, it's how thick and heavy a string I have, how many kilograms per meter of that string I would have. And I'm going to denote that by the Greek letter mu. I'm also going to do something far more fundamental, which is I'm going to go from our unrealistic picture of our string as being made of little bits of mass, delta m, separated by distance delta x. And I'm going to take the limit as delta x tends to 0. And we've got a continuous string again. And when I do this, what I've got in the brackets over here on the right-hand side of my equation just becomes a partial second derivative with respect to x. So I've got the change in y divided by delta x squared. That is, when I take the limit as delta x tends to 0, that is the very definition of a second derivative. So now I've got this rather beautiful thing. And what does it tell me? It tells me that the second derivative of y with respect to t only differs from the second derivative of y with respect to x by a constant, because both mu, the mass per unit length, and capital T, the tension in the string, they're both constants. So that means that there's something very similar in how y is changing with time as to how y changes with x along the length of the string. And the string can move in lots of ways, but however it moves, this must be true. So we have what's called the wave equation for the string. We call it a wave equation because it's very similar to equations which describe other things that you could call waves. So light waves, sound waves, and so on have equations that are in some way of a similar form. Okay, just rewriting slightly to tidy it up, so putting all the constants on one side, and this is our wave equation. Okay, that's that part done. Now all we've got to do is solve it. Now that we've got our wave equation for the string, we want to solve our wave equation for the string. And the key to this is this similarity in how y depends on time and how y depends on x, that's the distance along the string. Because d over mu is a constant, so we've got exactly the same thing on each side of the equation, except that on the right-hand side, it's multiplied by this constant. And as I've written here, differential equations like this are often solved by spotting the right form of a solution. So in this case, if I write y is equal to f of z, where z is kx plus omega t, then this is going to help me greatly. K and omega are constants, and in order for this to be a solution to this equation, we'll see that k and omega have to have the right values, and we will find the constraint on the values of k and omega. What are k and omega? What do they mean? Well, we can see that k somehow goes with x. It's got something to do with how y depends on x. So it's got something to do with, if you like, the wavelength of waves along the string. And omega has something to do with how y depends on t. So it's got something to do with the time period of the waves along the string, of how they depend on time. But that will all become clear later on. Right now, I want to show that absolutely any function, as long as the x and the t appear in this form and k and omega have the right values, will be a solution to our equation. So, first we're going to do a bit of chain rule. So if I ask myself, what is dy dx? Well, dy dx by chain rule must be equal to dz dx times dy dz. And dz dx, if you look at k, if you look at z, must just be k, because a partial derivative means that we're assuming time stays constant, so the omega t is a constant. That disappears when we differentiate, and the kx will just become k. When we differentiate again, and we can again do chain rule, so we can say d2y dx squared is d by dx of our previous result, k dy dx, and that must be equal to dz dx, which again is another k, times d by dz of k dy dz, so we end up with k squared d2y dz squared. If we do exactly the same thing, but now instead of differentiating with respect to x, we differentiate with respect to t. Then chain rule, same process, but instead of a k squared coming out, we get an omega squared. So, how has this helped us? Well, let's substitute in d2y dx squared and d2y dt squared results. What do we get? We get this. Omega squared d2y dz squared, so that's what d2y dt squared is equal to t over mu times k squared d2y dz squared. So that's what d2y dx squared is. Now that means we've got d2y dz squared on both sides. Now that means we can divide both sides by d2y dz squared and cancel it and end up with only constants in our equation. This is wonderful, of course, but we need to be a little bit careful, because if you divide by something, then that's not a valid step if d2y dz squared is equal to 0. Well, what would d2y dz squared be equal to 0 mean? Well, z depends on time, and it would mean that, therefore, d2y dt squared would be equal to 0. So, in other words, it would tell us there was no acceleration. So this is the situation where we have no resultant force, no acceleration. This is just simply our string being in equilibrium. So, fine, okay, string is in equilibrium. That's one possible solution. If we say, well, what happens when the string is not in equilibrium, then we can divide both sides by d2y dz squared. What we get then is omega squared is t over mu k squared, which means that the ratio of omega over k must be plus or minus the square root of t over mu. This plus or minus that we get when we square root is going to be important. Great, so this tells us that any function whatsoever of our z, of our kx plus omega t, will be a solution to our wave equation as long as omega and k are in the right ratio, which depends on these physical characteristics of the string, the tension in the string and the mass per unit length of the string. So, what does this mean? What does a function of this form look like? Okay, well, what I'm going to do is something a little bit strange now, but you'll see hopefully why exactly I've done it. What I'm going to do is rearrange this in order to get x as a function of y and t. Okay, a little bit strange, but let's do that. So y is some function of kx plus omega t. So that means that kx plus omega t must be the inverse function of y. Fine, so kx plus omega t is inverse function of y. So that means that kx must be inverse function of y minus omega t, so x is inverse function of y minus omega t divided by k. And x is a function of y and t. Okay, so what does that mean? Well, it means that if we ask ourselves what happens to x if we move time on by some amount delta t, so we replace the t by t plus delta t, then what we get is we get x as a function of y and t plus delta t is this thing. So I've literally just taken my t from here and I've replaced it with t plus delta t. And that's exactly the same as I had before, minus omega over k times delta t. So in other words, my x value is the same as my x value was before. My x value at which a certain y value occurs is the same as it was before, but with omega over k delta t subtracted. In other words, the whole thing has moved along by an amount omega over k in time delta t, omega over k delta t in time delta t. So it's moving along at a speed of omega over k. So the whole thing moves in the negative x direction at a speed of omega over k. So we can see that animated. So here I've got a function like this. It happens to be the function e to the minus kx plus omega t squared. And if I move time on, it moves in the negative x direction at a speed of omega over k. Okay, so far so good. So what we've found out is that absolutely any pulse of wave or continuous wave moving in the negative x direction at a speed of omega over k is going to be a solution to our wave equation. But of course, we said omega over k can be plus or minus t over mu. So it can also move in the same speed in the positive y direction. So in other words, instead of f, if we think of k and omega as being positive, y being f of kx plus omega t, we say that y is kx minus omega t instead. Then we do the same thing and we find that the whole curve moves in the positive direction at a speed of omega over k. We're making great progress here. We now have a whole family of solutions to our equation So it really can be anything, any shape of pulse or any shape of wave, providing it moves in either direction along at a speed of omega over k, then it's going to be a solution to our wave equation. We now have two whole families of functions which satisfy our wave equation. And we can show now that any linear combination of those must also satisfy our wave equation. So if I say in general y is equal to some constant a times a function which satisfies my equation, plus some constant b times another function that satisfies that equation, plus we could keep this going with more functions, then when I differentiate that twice with respect to t, the constants of course just stay there, and when you differentiate a whole load of functions added together, you can just differentiate them separately and add them together. So d2y dt squared is just a times d2f1 dt squared plus b times d2f2 dt squared, etc., etc. d2y dx squared takes the same form, so provided that f1 and f2 separately satisfy our wave equation, then the linear combination of them will too. So this is great. This means that we can write down what we've got so far in one very neat form which is completely general. And that is this. Y is f1 of kx plus omega t plus f2 of kx minus omega t, where f1 and f2 are any functions at all. Now I don't have constants a and b in front of those because those could be absorbed into our definition of f1 and f2. So if f1 was sine kx plus omega t, well, we could always make f1 be equal to 2 sine kx plus omega t, for example. So we don't need to worry about writing constants separately. This is general. All right, it's kind of too general. When we pluck a string, physically, something predictable happens. What we've got here is an infinite variety of possibilities for things that could happen to our string. So clearly what we need to do is apply some boundary conditions. So boundary conditions means more things we know about our system which help to cut down our possible outcomes and tell us what really will happen. So the first thing that we know is that the ends of our string are fixed. So at x equals 0, the string cannot move. Y must be equal to 0 at all times t. And at x equals L at the other end of the string, we can also say the same thing. So let's apply the first of these conditions. So at x equals 0, y equals 0 for all t. So in our general solution here, I'm going to replace my y by 0 and also my x by 0. And what do I get? I get this. So 0 is equal to f1 of omega t plus f2 of minus omega t. So this gives us straight away a relationship between f1 and f2, because this has to be true for all t. So this isn't something that just happens to be true at one special value of time. It's something that's true at all values of time. So in other words, it doesn't matter what is the value of the variables that f1 depends on and f2 depends on, they must always be related in this way. So we can write that f2 evaluated at any value of kx plus omega t or kx minus omega t must be equal to minus f1 evaluated at minus that same value. All right, so we can substitute this in. So y is equal to f1 of kx minus omega t minus not a different function f2, but the same function, but evaluated at minus kx minus omega t. So in other words, which is minus kx plus omega t. All right, this is wonderful. We've got great stuff happening here. Instead of two different entirely arbitrary functions, we've cut it down to one now, just by applying the first boundary condition. So I'm going to stop labeling that function f1 because we don't have f1 and f2 anymore, and I'm just going to call it f. So here it is. Now let's apply the boundary condition that at the other end of the string is also fixed to the guitar there as well. So when x equals L, where L is the length of the string, then y is also equal 0 for all time. So substituting in that, I get y is 0, so I can replace my y with 0, and I can replace my x with L, so I get this. Okay, so far so good. Now omega t can take any value at all, because this has to be true at all times t. So it is generally true of this function that f of z plus kl is equal to f of z minus kl for all values of z. And f of z plus kl is the same thing as f of z minus kl plus 2kl. So just take a moment to think about that, to process that. If we take z minus kl plus 2kl, we get z plus kl. So this is the same thing as we've got in the line above. Why is it useful to write like this? Well, because z can take any value, z minus kl can take any value. So I can replace z minus kl just with z, and I can say f of z plus 2kl equals f of z. This is what's called a periodic function. It's a function that repeats itself every time the variable goes up by a certain amount, and that amount is 2kl. So we have found that this function f, we've cut it down to one function by applying one boundary condition, and by applying the second boundary condition, we've found that the function f must be periodic with period 2kl. We now know that this function must repeat itself every 2kl. And this is a mathematical condition on the function f. This isn't just about how f changes with x, even though that's how we derived this condition. It's also going to tell us something about how f changes with time. So firstly, let's think about what it tells us about how f changes with x. Well, it must repeat itself every 2kl. But it could repeat itself more frequently than that. As long as it gets back to where it started after 2kl, it could repeat itself every time z goes up by kl, or every time z goes up by 1/3 of kl, or whatever. In other words, we can say it could be periodic with any period 2kl over n, where n is a whole number 1, 2, 3, etc. Because that would imply that it's also periodic with a period 2kl, which it must be. Okay, so if it's periodic with a period 2kl over n, then what happens when we look at one particular moment in time and we move along the string by an amount delta x? Well, it means that y of x plus delta x and t is equal to this. If I substitute in x is x plus delta x, I get an extra kx here and an extra minus kx here. Or, sorry, extra k delta x and an extra minus k delta x. Now, if k delta x is equal to the period, so if k delta x is equal to 2kl over n, then what I get is this. And when I look at this, what's in this bracket here is the same as what's in this bracket up here, but plus moved on by 2kl over n. In other words, it's got to be that the function has the same value, because we know that when we move on by 2kl over n, the function repeats itself. So this first term, f of kx plus omega t plus 2kl over n, is just the same as the first term here, f of kx plus omega t. And similarly, if I look at this bracket here, it's been moved in the opposite direction. It's been stepped back by 2kl over n. And if the function repeats itself every 2kl over n, then when you move a step back of that amount, it also must be the same value. So we can say it's equal to this, which of course is just y of x and t. So in other words, what we've got is something that, providing k delta x is 2kl over n, then we get back to where we've started. So that means the function is such that y has a wavelength along the string of 2l over n, because here the k's on both sides will cancel. So delta x is 2l over n will lead to everything repeating itself. So we have found that the wavelength of any waves that are set up on our string must be 2l over n, where n is a whole number. Now we can do exactly the same thing, but applying what we know to the time dependence of y. So if we do the same thing again, but instead of moving on x and keeping t the same, we're going to keep x the same. We're going to look at one point on the string, and we're going to say, how does it change when you move on time by an amount delta t? Well, when you do that, you shift this by plus omega delta t, you shift this by by also plus omega delta t. So if omega delta t is 2kl over n, then we're going to get back to where we started again. And if we divide both sides of this by omega, we now get a time period of 2kl over n omega. So this is really important because it means we've found out about the time dependence of y. All right, so far so good. We can also now know the frequency. The frequency is just 1 over the time period, because time period is how many seconds it takes for one whole cycle to happen, and the frequency is how many cycles there are per second. So that's just 1 over the same thing. So if the time period is 2kl over n omega, that means the frequency is n omega over 2kl, which I've written like this, n over 2l omega over k. But we know what omega over k is. We know that omega over k has to be equal to plus or minus root t over mu. And if we're going to say that omega and k are both positive values, then omega over k is root t over mu. This brings us to our beautiful final answer, which is this formula for the frequency of the oscillations of the string, and thus the frequency of the notes made by the string. So let's remind ourselves what everything is. So L is the length of the string, T is the tension in the string, mu is the mass per unit length of the string, and this number n, which can be any whole number, when n is 1, we get the lowest frequency, which is called the first harmonic, and is the note that the guitar plays. When n is a higher number, 2, 3, 4, etc., we get the second, third, fourth harmonic, which all add in various amounts to give the rich sound that the guitar makes. Let's just take a moment to appreciate what we've got here. We have derived, just from Newton's second law, a formula that tells us everything about the guitar. So L tells us about playing the guitar. When we fret the strings, what we're really doing is changing the length of the string that we're allowing to oscillate. T tells us about tuning the guitar. So when we turn the tuning pegs, we are changing the tension in the string, and mu, of course, tells us about the choice of string itself, the thickness and heaviness of the string. That's where I'm going to end the mathematics. Now I just want to go on and show you a few fun things that you can do with to extend what we've done so far. So we can ask ourselves, how much of each of these harmonics do we get? What is going to be the amplitude of each of the original harmonics? Well, that depends on how we pluck the string. So if I think of plucking the string as simply pulling part of the string upwards, so it makes a sort of triangular shape, and you might notice it's not a perfect triangle that I've got at the moment, and I'll explain why in a moment. Now, of course, I'm massively exaggerating the amplitude to which I pluck the string in order to make everything more obvious on the diagram here. But what we can do is we can take this, imagine it repeating itself continuously even beyond the length of the string, and then, because that's a periodic function, by a process called a Fourier series, you can model that as an infinite sum of sinusoidal functions. So we can say that if we add together this first harmonic and this second harmonic, which is actually 0 at the moment when the string is plucked exactly in its middle, and then a third harmonic with this amplitude and 0 fourth harmonic, and a fifth harmonic with this even smaller amplitude, and so on, then those added together will give us our triangular shape of string. And the reason that I don't have a perfect triangle is because what I've actually got is the sum of all my harmonics. So I haven't got an infinite series, I've just got quite a few of them there, and it's only an approximation to a triangle. So okay, that's what I do when I pluck the string, and that gives me the relative amplitude of the harmonics initially. It doesn't tell me what will happen to those harmonics over time. Will they all die away at the same rate, or will some of them persist more than others? So there are lots and lots of interesting questions going on here. What happens if I don't pluck the string exactly in the middle? What happens if I pluck the string nearer to one end? Well, we can see that those even-numbered harmonics start to come into it. So before we only had the first, the third, the fifth harmonic. Now we've also got the second, the fourth, and the sixth harmonic, and so on. And it changes the relative amplitudes of each of them. Here's the same thing illustrated in a different way. The red dot here shows where I'm plucking the string, and this bar chart shows the relative amplitudes of the different harmonics. At the moment, I'm plucking it dead in the middle, assuming that I'm playing an open string, unfretted, but more realistically, I would probably pluck over the sound hold of the string, something like that. And then I'd get that interesting mix of harmonics there. Of course, we've only thought about the string so far. Then the body of the guitar and the air inside that space, there are going to be waves and oscillations set up within that are going to amplify some of those harmonics more than others. So that's going to change things too. So what we've done here is a really good start in getting an intuitive understanding of what's going on, but it's only the start. I'd also like to point out that what we've done is much more than just think about guitar strings. The methods that we've used, setting up differential equations and solving them and applying boundary conditions, and in particular the wave type equations and the stationary wave solutions that you get to those with boundary conditions, have all sorts of applications that are nothing to do with musical instruments. Even things like deriving the energy levels of atoms using quantum mechanics, thinking of them as bound solutions of the wave functions of electrons. So this has all sorts of applications. If you followed this video, then it's going to make learning lots of other bits of physics much easier, hopefully. Thank you very much. I hope you've enjoyed it, and I'm going to leave you there.